Ladies and gentlemen, good morning. Let's continue with our module in heat and mass transfer. We are using the textbook of Sengel and Gajar, and we are busy with chapter 8, which is on internal forced convection. If you look at the chapter, you'll see that it has 6 parts. The first few, the introduction we've completed, the average velocity and temperatures, and the entrance region. Today we're going to do paragraph 8.4, which is the general thermal analysis, before specifically looking at paragraph 8.5, laminar flow in tubes, as well as paragraph 8.6, turbulent flow in tubes. Now this paragraph 8.4 is really the most important paragraph in this chapter. And it looks very simple. There are lots of equations to be used, but when you're going to get to practical applications, what is very important is you must be able to distinguish between problems where we've got constant heat flux and problems where we've got a constant wall temperature. And if you cannot do that, you're just going to put in values into the wrong equations and the wrong formulas, and you're going to end up with the wrong solution. So fundamentally, this is not very complicated, the work I'm going to do with you, but it is very important that you understand it very well. Okay, so paragraph 8.4 is the general thermal analysis. Oh my goodness, it's not working. Is it not working here? Oh, is it making noises? Right, okay. Thanks, Tamara. Okay. Right. The general thermal analysis. What is very important is you have to distinguish between problems of constant heat flux and constant temperature. Constant heat flux we are going to indicate with a Q dot. The heat flux is constant, and problems where we've got a constant wall temperature with a T. Today in this lecture we are going to concentrate on this one, and if we have time I'm going to start with this one, but most probably we will not be able to complete it. So it is 2 different approaches. First one, we're going to look at this one and then at that one. The one thing that both of them have in common is that it is about flow through something, an internal geometry. And just to make it easy, we identify it as if it's like a tube with an inlet temperature there, Ti, and a mass flow rate m dot, and here is the outlet temperature Te. T for exit, outlet temperature. With all these problems, we normally have a temperature which is an average temperature for the fluid, Tm for mean, and then we've got a surface temperature, Ts. That is now on a micro scale. So if we look at this, then for all of these problems, we have 2 things that we can say. Firstly, we can say that the heat transfer rate is equal to the mass flow rate, Cp, multiplied by the outlet temperature minus the inlet temperature. Very simple equation. What we can also say is that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface temperature, the surface area, multiplied by the temperature S minus Tm. Those are the 2 general equations which are always valid. However, if you think back of the lecture of yesterday, the thing that complicates this is the heat transfer coefficient. Because the heat transfer coefficient in the lectures of yesterday, I've showed you that the heat transfer coefficient at the inlet is very high, and then it would decrease until it is fully developed. So it is not always a constant. Okay. So this might be a constant, or actually is a function of x, and these temperatures are not constant because they change depending on the fluid temperature. So that is the complications that we have to consider. So let's look now at the case of the constant heat flux. constant heat flux case, like that, or sometimes in the footnotes or the subscripts, no, not T, sorry, we indicate it with an H, sorry. So sometimes in the subscripts we indicate it with an H. For problems with a constant heat flux, if we would go and generate a graph of what is happening, of the temperature as a function of X, for a tube or any geometry through which flow occurs. Okay. Where this is the inlet temperature and that is the outlet temperature, and we've got the constant heat flux like that. So there's our constant heat flux. We show it schematically like that. For these types of problems, the constant heat flux is equal to the heat transfer rate divided by the surface area. And the units will always be in watts per square meter. Watts per square meter, and typical applications would be electrical resistance heating, nuclear reactions, and one as well as solar radiation. Those are three typical practical applications where you will have a constant heat flux. Now what we would like to do, what this lectures would be all about, the lecture of today as well as the next one, is to actually find the surface temperatures of the tube and or the temperatures of the fluid as it flows through our geometry. We would like to know what is happening on the inside. And how we do it is, let's start with the fluid temperature. If we look at the fluid temperature, we've got this equation which actually tells us that the heat transfer rate is equal to the heat flux multiplied by the surface area is equal to the mass flow rate Cp multiplied by T outlet minus T inlet. So by solving the outlet temperature, we can write that the outlet temperature is equal to Ti plus the heat flux multiplied by the surface area divided by the mass flow rate and Cp. Okay? The surface area is equal to P, the perimeter P multiplied by L of the heat flux. And therefore we can write it as the inlet temperature plus the heat flux multiplied by PL divided by the mass flow rate Cp obviously this would only be valid for that is in general valid, but for the special case of a circular tube, the surface area would be equal to pi multiplied by the diameter multiplied by L. Do you agree? So we can also write it as inlet temperature plus the heat flux multiplied by pi dl divided by the mass flow rate Cp. And I'm making this drawing to indicate to indicate it is only valid for a circular tube. Okay, now if we take a look at this equation and we would say, well, the inlet temperature is known of the fluid and we want to get the outlet temperature, then it says the outlet temperature is equal to the inlet temperature plus the heat flux, which is a constant, by the diameter, which is a constant, as well as the length. It's a constant divided by the mass flow rate and the Cp. So we can solve everything from this. Do you agree? So therefore, if that is T inlet, then that would be T outlet. So we've got the outlet temperature by using this equation. Now if we take a good look at the equation, this is L. If we want to know what the temperature is going to be halfway through here, okay, then we can also use this equation, because the constant heat flux means the temperature increases constantly according to this. So we can actually write this temperature as the mean temperature at any specific point x is equal to Ti plus the heat flux pi dx divided by the mass flow rate and Cp. Rewrite it a little bit so that we can write it as the heat flux pi dx divided by the mass flow rate Cp plus Ti. And if you take a good look at it, you will see it is an equation for a straight line. So that is equal to the gradient mx plus c. Okay. So this equation tells us that you can use it to determine the outlet temperature, but you can use it to determine the temperature wherever you want in the tube. So to indicate the fluid temperature, I'm going to use blue. Okay. It means that the solution is a straight line of the fluid. The average fluid temperature is doing that. It increases linearly. Yep, question.
So the Cp, if it varies with temperature?
Yes, you're right. It is obviously not perfectly correct because Cp is a function of temperature. Again, it depends on the range over which the heating occurs. If it is really a lot, then it is not constant. But what you then can do is you just need the equation for Cp as a function of x. And you can put it in here, you can still plot the temperature along, the mean temperature along the tube. Okay. Okay, now, we actually know everything about the fluid now. So that is one part of the problem. The other part is we need the surface temperature. So let's look at the surface temperature, if we can determine the surface temperature. We determine the surface temperature by saying that the heat transfer rate is equal to the heat transfer coefficient multiplied by the area multiplied by Ts minus Tm. Or the heat flux multiplied by the surface area is equal to the heat transfer rate is equal to everything there on the right hand side. Well, let me write it out. HA Ts minus Tm, and we can get rid of the areas, and then write that the heat flux is equal to the heat transfer coefficient multiplied by Ts minus Tm. Right, so if we look at this equation, we see that we can determine the surface temperature everywhere. Okay, because we can determine the value of the fluid temperature everywhere. Do you agree? Okay. However, there's one complication, and what is the complication? The complication is our heat transfer coefficient is not a constant. Going back to the lecture of yesterday, we've said that the heat transfer coefficient as a function of x, there's the fully developed flow and there's the developing flow. So in the developing part of the flow, the heat transfer coefficient is not a constant. However, if the flow is fully developed, then the heat transfer coefficient is a constant, which means that we can actually determine, in many cases, if the flow is just fully developed, the outlet surface temperature, if we obviously can get the heat transfer coefficient. The best is to look at this problem as if it is a problem, an example. So, in this example, we are going to have the inlet temperature, Ti, as 20 degrees Celsius. It's going to be water flowing through here. The mass flow rate is equal to 0.7 kilograms per second. The Cp value of the water is 1080 joules per kilogram Kelvin. It doesn't matter which fluid it is. The length of the tube is 5 meters and the diameter is 10 millimeters, and the heat transfer rate is by radiation and it's 50 kilowatts. So the question is, what we have to determine is what is the surface temperature and the fluid temperature for, if we give the following details. That is the heat transfer coefficient, and at 2.5 meters it's going to be fully developed, so halfway through the tube. This is 5 meters, that's the total length, and here is 1 meter, so that is x. From 2.5 meters to 5 meters, the heat transfer coefficient is 10,000 watts per square meter degree Celsius. And at this point here, the heat transfer coefficient is 30,000 watts per square meter degree Celsius. So this is given. Can you understand the problem? Okay. So looking at the fluid temperature, from that, you don't even have to derive it. You can just work it out from first principles with 1 or 2 steps. The outlet temperature is equal to the inlet temperature plus the heat flux multiplied by the surface area divided by the mass flow rate and Cp. And the heat flux is equal to the heat transfer rate divided by the surface area. The heat transfer rate is 50 kilowatts, so it's 50 multiplied by 10 to the 3, divided by the surface area, it's pi multiplied by 0.010, 10 millimeters, multiplied by the length, which is 5 meters, and from that we can determine the heat flux as 318,300 310 watts per square meter, or 318 kilowatts per square meter. So that's the heat flux. Okay, so we can calculate the outlet temperature as the inlet temperature, which is 20, plus the heat flux, which is 318,000, multiplied by the surface area, which is equal to pi multiplied by the diameter, multiplied by L, divided by the mass flow rate is 0.7, and Cp is 1080, and that will give us an outlet temperature of 86.14 degrees Celsius. So if this temperature is 20, this temperature is 86.14 degrees Celsius. Okay. But taking a look at that formula, we would actually also like to have the fluid temperature at 2.5 meters and at 1 meters. So in general, we can say for that equation, we can write it as the fluid temperature at any point x is equal to Ti plus the heat flux multiplied by the surface area, and the surface area is pi dx, divided by the mass flow rate and Cp. If we do the substitution, it is equal to 20 plus 318 kilowatts multiplied by pi, 0.010 multiplied by x, divided by the mass flow rate, which is 0.7, and Cp, which is 1080. And we can write it as a general equation as 13.23 times x plus 20. So there's the gradient of the line, and that is the intercept, which is 20. Very simple. So with this general equation, we could have derived it from the beginning and then used it to determine the temperature at 5 meters, but now we're going to do it at 1 meters and at 2.5 meters. So in general, we can say the average fluid temperature, where x is equal to 1, is equal to 33.2 degrees Celsius. At 2.5, it is equal to 53.08 degrees Celsius. And at 5, it is equal to 86.14 degrees Celsius. Going to our graph, if that is approximately 1 meters and that is 2.5, it means that this temperature there is equal to 33.2, and that temperature there is equal to 53.08 degrees Celsius. Very simple. Any questions? Comfortable with it? Good. Now let's go and determine the surface temperatures now. The heat flux is equal to the heat transfer coefficient multiplied by Ts minus Tm as a general equation. Okay. Tm is a function of x. Okay. We want to know Ts, so we can just write Ts is equal to the heat transfer rate divided by the heat transfer coefficient plus Tm as a general equation. This equation is that equation. So we can write it as the heat flux divided by the heat transfer coefficient plus 13.23 times x plus 20. Now we can go and solve the surface temperature at any point x. Okay. So if we go and solve the surface temperature at x equal to 1, the surface temperature is going to be the heat flux, which is equal to 318 multiplied by 10 to the 3, divided by the heat transfer coefficient at 1 meters. 1 meters, the heat transfer coefficient is 30,000. Divided by 30,000 plus 13.23 times x is 1 plus 20. And that will give us a surface temperature of 43.81 degrees Celsius. We can now do the same at 2.5 meters. 2.5 meters, the heat flux is still the same, 318 kilowatts per square meter, divided by the heat transfer coefficient, which is now equal to 10,000. The heat transfer coefficient is now 10,000 plus 13.23, x is 2.5 plus 20, and that will give us a surface temperature of 84.91 degrees Celsius. Lastly, for x equal to 5 meters at the outlet. Again, the heat flux is a constant, 318 kilowatts. The heat transfer coefficient is fully developed between 2.5 meters and 1 meters. It is still 10,000. But it's going to increase because the fluid temperature increases. Plus 20, and that is 117.97 degrees Celsius. Are you all comfortable with that? It's very simple. Let's go back to the sketch to really indicate now what is happening here. If you go back to the sketch and you go and plot this graph, and I've done it just for 3 points, but you can go and do it for 10 or whatever, then you're going to see that this line of the surface temperature has the same gradient as this line. And the surface temperature does something like that. Okay, so that is the surface temperature. So if we look at the temperatures, this temperature is 117.97. That surface temperature is 84.91, and that one is equal to 43.81. Coming back to this equation, the heat flux is equal to the heat transfer coefficient multiplied by Ts minus Tm it means that Ts minus Tm. Ts minus Tm, what is it? Ts minus Tm is the difference between those two temperatures. Okay. So Ts minus Tm is equal to the heat flux divided by the heat transfer coefficient. So if we go and calculate Ts minus Tm for these three cases, then this Ts minus Tm is going to be 10.61 degrees Celsius, and this one is going to be 31.83 degrees Celsius, and this one also 31.83 degrees Celsius. Thus, you can see this temperature difference is constant. Going back to my sketch, and my sketch is not a good example of how it should be, but that temperature difference and that temperature difference is therefore the same. So this delta T is equal to 31.83, and that delta T is also 31.83 degrees Celsius. While this delta T would be equal to 10.61 degrees Celsius. That's theoretically, at the inlet, the heat transfer coefficient should be infinite. Why? Because the boundary layer thickness is 0. Which therefore means that these two temperatures there should be about the same. Therefore, while the flow is developing, remember, while it is developing, in this area, the heat transfer coefficient is larger than when it is fully developed. So because the heat transfer coefficient is larger, the temperature difference is smaller than here. But as the heat transfer coefficient decreases, okay, as it decreases, the temperature difference starts becoming the same. So from this point onwards to that point, the surface temperature differences, or the difference in temperature between that, maybe my graph should have been more something like that. Now it looks a little bit better. Okay. So this temperature difference and that temperature difference is a constant. You all follow that? Yes, question?
So would that be due to Hall effect? Would that be due to sort of secondary effects that you discussed yesterday, like say your internal eddy flow and all the rest of that?
No, not yet. In this chapter, specifically in the laminar flow, we're going to assume the flow is what we call forced convection only. So there's no secondary flow. Okay, it is just forced convection, and then this is valid. The secondary flow, in terms of the developing of it, hasn't been fully described yet in terms of easy equations. So to walk the whole path, we do this chapter and we assume the flow is forced convection only. In the next chapter, we're going to incorporate the mixed convection, and it is only after that that you have all the tools where you can take secondary flow into consideration. Okay. So for this, we assume it is forced convection only. But coming back to your question, what typically happens if you look at the Nusselt number as a function of x of d, okay, is that at the inlet, the flow would be what we call forced convection flow, and the results would actually do something like that. That's a Nusselt number of 4.36. We are going to do that in the next paragraph. So for forced convection, you actually get something like that, and if it's fully developed, it is equal to 4.36. Now flow would follow this line at the inlet until the secondary flow starts. And when the secondary flow starts, the heat transfer coefficient increases. Okay. So it's going to increase, but it cannot increase all the time. So the secondary flow starts as small and slow circles, then they accelerate until they are fully developed. And once they are fully developed, they do something like that. So in terms of your theory for forced convection, where you're going to assume the Nusselt number is 4.36, when you have secondary flow, this Nusselt number can easily be in the order of about 8 to 10, which means it is more than 200 to 300% more than that of forced convection. This work, a PhD student of mine, Marilise Everts, has actually, she's completing a PhD on this, and in that work we are actually predicting these areas where the transitions occur from the forced convection to the mixed convection to the mixed convection fully developed. Okay. Any other questions on this theory? Okay, so let's go to the next part, which is the part of constant surface temperature. Okay, constant surface temperature. If we look at this case and we plot again the fluid temperature and the wall temperature as a function of x. So that's the inlet temperature and that is the outlet temperature. And what we now have is Ts is equal to a constant. These types of problems occurs during phase change, during boiling, during condensation, and during evaporation. So if you're interested in heating, ventilation, and air conditioning, you need to take note of that. If you're interested in the generation of electricity with a nuclear power plant, you will always have two-phase flow. You will have boiling and condensation. If you do it with a CSP plant, concentrated solar power, again, it's a very important application in industry. Okay, now, again, we are interested in getting the surface temperature and the temperature of the fluid. Because when we have that, we can really understand what is happening. Now, with the case of a constant surface temperature, one half of the problem is given, because the surface temperature, Ts, is a constant. And I'm showing the problem as if the surface temperature is higher than that of the fluid temperature. It might, of course, be that this temperature is there. Might be lower than that of the fluid. And let's suppose that is the inlet temperature, Ti, of the fluid. For this case, we would like to get the outlet temperature. So, let's suppose we do have the outlet temperature like that. Then with the background that we have up to now, most probably we will say, well, this is a simple problem. All I'm going to do is I'm assuming a straight line between these two, and that temperature there is the bulk temperature is equal to the inlet temperature plus the outlet temperature divided by 2. And with that, we're going to say that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by a delta T, and this delta T is called the delta T average. I'm going to explain it just now. Again, we can write it as the heat transfer coefficient multiplied by the surface area multiplied by Ts minus Tm, or the heat transfer coefficient multiplied by the surface area Ts minus T bulk. Now, the problem with this approach is that normally it is not correct. Because if we have a case where we've got a wall temperature that is constant, then this temperature at the beginning would increase significantly because there's a huge temperature difference. But as the flow through the tube, the real temperature distribution will do something like that. So if we look at this approach by saying that, but this temperature difference is delta T average, it shows that that approach is not valid. It is not accurate at all. So using this approach, we should say that we have to be careful for doing that. There are cases where you can do it. Maybe this tube is very, very small. Then your error wouldn't be that large. But in general, it doesn't work. So to make it work, there's a derivation in your textbook that typically now looks at a control volume. And in this control volume, that distance is dx. And the mass flow rate through here is m dot Cp multiplied by Tm, or the energy transfer going into the control volume, and there it will go out as m dot Cp multiplied by Tm plus dTm, and the heat transfer through there would be equal to delta Q is equal to the heat transfer coefficient multiplied by Ts minus Tm, and it is of course assumed that this temperature Ts is equal to a constant. Okay, now I'm not going to show you the whole derivation, but the derivation is based on looking at the heat transfer rate in is going to be equal to the heat transfer rate out. And you're going to end up with an equation looking like this: m dot Cp dTm is equal to the heat transfer coefficient multiplied by Ts minus Tm dAs, and where AS, of course, again is equal, dAs is equal to P, the perimeter, multiplied by dx. And looking at this equation, you're going to end up with an integration that needs to be conducted between the inlet and the outlet of d Ts minus Tm divided by Ts minus Tm is equal to minus the heat transfer coefficient multiplied by P divided by the mass flow rate Cp, integral from 0 to L dx. Okay, now this can be integrated so that you can get the ln of Ts minus Te divided by Ts minus Ti is equal to minus the heat transfer coefficient multiplied by the surface area divided by m dot Cp so that we can derive a general equation giving the fluid temperature as a function of x as Ts minus Ti e to the minus Hpx divided by the mass flow rate and Cp. So this is a general equation that can be derived. Okay. It gives the fluid temperature as a function of x is equal to the surface temperatures minus the inlet E to the minus HPX divided by the mass flow rate and Cp. There's one thing in this derivation which I hope you see that you should not be comfortable with. Okay. And what is that one thing? It has to do that in this derivation, the assumption is made that the heat transfer coefficient is a constant, and it's not a constant. I'm showing that to you all the time. If the flow is developing, it is not a constant. So this is at the moment the best simple analytical equation that can be used to determine this outlet temperature and to determine the temperature everywhere along that tube. Okay, the other thing that is very important in this equation is this term. This term is also called the number of transfer units. The number of transfer units, and that is equal to the heat transfer coefficient multiplied by the surface area divided by m dot Cp. If we go and look at the values of NTU in an equation which is TE is equal to TS minus TS minus TI e to the minus NTUs. So this term is just NTU, e to the minus NTU. If we take that inlet conditions that we have there with the heat flux, etc., we don't have the heat transfer coefficients. And let's suppose the NTUs is equal to 0.01. Then the outlet temperature is going to be 20.8 degrees Celsius, which means there's almost no heating occurring in the tube. The inlet temperature was 20, and over a distance of 5 meters, it only increases to 20.8, so almost nothing. If it is equal to 0.5, the outlet temperature is going to be 51.5. So now there's increase of 30.5 degrees Celsius. If it is equal to 1, then it is going to be 70.6. If it is equal to 3, it's going to be 99.2. If it is 5, it's going to be 99.5. And if it is 10, the outlet temperature is going to be 100. If you look at this very critically, and you're in the business of designing heat exchangers, okay, what should you observe? And not enough attention is given to that normally in textbooks. So what you should observe is that if the NTUs start getting to 3, the increase in temperature is going to be almost nothing. So to increase the temperature with another 0.8 degrees Celsius, you will have to make the tube length almost 3 times longer. Okay. So normally, 3 is a good rule of thumb. If you do a problem and the NTUs is 3 or 5 or something like that, you can immediately know what the outlet temperatures should be. It means that that outlet temperature and that temperature should meet each other. Okay? Which means in that significant part of the heat exchanger, there's no heat transfer rate occurring. Okay? So in general, 3 is a good rule of thumb. Any heat exchanger, if the NTUs is more than 3 or more, then you're wasting material and money. Okay. Right, ladies and gentlemen, thank you very much.